Okay, we'll go ahead and get started. So today, and I know a lot of you guys have already kind of seen this and figured it out in your homework, but we'll formally talk about it. We're going to talk about coordinate descent. So so far we've covered root finding methods. And so root finding methods allow us to find where a function is equal to 0, despite the computer not having any kind of understanding of algebra, these symbolic representation. We just say, just keep following these steps, and a lot of the times, not all the time, but a lot of the times, it will succeed to find the spot where the function equals 0. And then we built off of that and said, well, if we apply this to a derivative, then we can find where a function has a local min or a local max, okay? And we said, well, if we had trouble finding a derivative, we also have a numeric method that allows us to estimate the derivative, okay? So we have a bunch of these numeric methods that give us kind of solutions to a lot of other problems where the traditional approach always required algebra and or calculus. Okay. Today we'll take a look at a multi-dimensional problem. Okay, so far everything's been unidimensional. Find where one function is equal to 0 or where one function has a local min or local max. And today we'll look at what if you have a function of 2 variables, or what if you have a function of more than one variable. So so that's what we have. So coordinate descent is an optimization method for multidimensional functions. And the basic premise is this. Take your multidimensional function, and you can think of the multidimensional function as, so if you have a 2-dimensional function, you can just think of it as a bunch of 1-dimensional functions, but just at kind of like different slices, okay? So you might have some function f of x, y, and we'll just, what do I have? I have x squared minus 2x, I'm just making this up, minus 1/2 xy plus 2.5 y squared. Okay, and when you graph this, this is some kind of paraboloid, okay? So you can think of it, I don't know. I'm not very good at drawing this stuff here, okay? But we have basically a bowl, right? And the idea is this thing exists in 2 dimensions, right? You have your x, I'll do this is y and this is x, and this is going to be your kind of your z, okay? And what we want is what is the minimum of this function? Okay, so we want to find this location right here. And what we'll do is we'll start at some arbitrary point, start at an arbitrary x0, y0, start in an arbitrary coordinate. Okay, and then so we'll just say we'll start like right here on this side of the parabola. And what you'll do is you will reduce this 2-dimensional function into a 1-dimensional function by holding one of those variables constant, okay? So we hold one of the variables constant, okay? And this reduces a 2D function to a 1D function, okay? And so I think in this thing I started off at -1, 1.5. Okay, so we'll just start at, x0 is -1 and y0 is 1.5. And then we'll hold y constant at 1.5. Okay, so if I hold y constant at 1.5, basically I'm going to say, this is y equals 1.5, and I'm going to take a plane and I'm going to just slice the parabola right here, okay? And when I do that, this is what we get. It's hard, okay? So I'm just slicing the parabola, okay? Or paraboloid. So you can imagine this bowl here, and I'm just saying we're gonna just take this sheet at y, the plane, y equals 1.5, okay? And we're gonna just slice the paraboloid right there, okay? And when you slice that, you'll get a parabolic shape, okay? And it's a function of just x. And what we want is we want to find the minimum of this function. So we're going to, so this reduces the 2D function to a 1D function, okay? So we will hold y constant at y equal to 1.5. So my function, which was this, okay, at basically y equals to 1.5 will reduce to x squared minus 2x minus 1/2 x times 1.5 plus 2.5 times 1.5 squared, okay? So what is this? 1/2 times 1.5 is minus 3/4. So I get x squared minus 2.75x, is that right? Plus, I don't know, whatever this turns out to be. I need a calculator. So 1.5 squared times 2.5, 5.625, okay. So this becomes just a function of x. And so now we want to know, okay, where is this function minimized? Okay, so let's find minimum of this function. All right, if we had to do this by hand, this is easy. We just say, well, let's set f prime of x equal to 0. So that becomes 2x minus 2.75 is equal to 0, right? And we get x is equal to 2.75 over 2, and you get x is equal to 1.375, okay? If we don't have calculus, right? We can just use the computer to find the minimum of a unidimensional function. All right, so we could use any of the methods that we've employed. I think in the homework I have you guys use golden, right? And I just say, and you just, so if we use golden, the golden section search, then it will also say x is 1.375. Okay, and so that in our diagram is effectively, it's going to say, all right, the that's at the bottom of this parabola right here. Okay. All right, and so that updates. So now now we update x1 to be 1.375. Okay, and so here is again. I don't know. This is hard. Okay, and so now we've updated our diagram, and we are now located right here. Okay, where x is equal to 1.375, and then now we take a plane and we slice it in the other direction. Okay, so we take a plane and we slice it in the other direction, and when we do that, it says, you know, I don't know what this thing looks like, but this is what probably, I don't know, looks something like this. Okay, so we take a slice of the bowl in this direction, and then we find the minimum there. Okay, and we just iterate back and forth, and that's basically it. I'll maybe I can demonstrate a little bit better with some computer-drawn graphics and stuff. All right, and I'll post my code up here. And so we just iteratively turn the functions into one-dimensional functions by holding basically the other variables constant. So here it's just a two-dimensional function. So if you hold one variable constant, then it becomes a one-dimensional function. But this can be applied to like a five-dimensional function, okay? And basically you would hold, if it's five-dimensional and you have variables a, b, c, d, e, you would hold b, c, d, e constant and it would become a function of just a, and you find the coordinate of a that minimizes this function of a. Then once you have that, you update a, and then you hold a along with c, d, and e constant, and it becomes a function of just b. And then you find the value of b that minimizes that one-dimensional function. And then you just iterate through all of the variables one at a time, holding a constant, holding everything but a, holding everything but b, holding everything but c constant, everything but d constant, and everything but e constant. But it's hard to graph functions of more than 2 dimensions because we can only really see in 3 dimensions. So yeah.
For a symmetric paraboloid, it'll only take 2 turns to get the actual minimum, right?
Not always. If the paraboloids, I guess, major and minor axes are parallel to the x and y axes, then yes, it'll only take 2. But if you think of kind of the ellipse, and if that is not parallel to the x and y axis, then it'll take more than 2. Yeah. Okay. So to draw this, I'm using a package called Plotly. We didn't cover this, but it's fine. You guys, you can look it up. It's fairly new. I don't even know how to use it very well. You know, they're constantly coming out with new stuff, right? So I used to use a package called Graph 3D, but this is nicer. Okay. And then I'm sourcing the golden section search function, which is part of your homework already. That's already in there, okay? And so here's our two-dimensional function. I guess I called it g, okay? X squared minus, oh here, let me zoom in. In class, I always zoom in, and then when I get back to my desk, it's like, and I plug in my monitor, it's like gigantic, and I have like 5 lines of code here. Okay. All right. So we have G, right? And so just to use Plotly, I'm going to create a sequence of x and y values, and then and I use the outer function. I apply that to x, y, and g, and that's going to return a matrix where, so just so we can see, x is this vector, you know, negative 1.5, kind of incrementing by 0.5, and so is y. And if I just plug in x and y into g, negative 1.5 and y is negative 1.5, then it spits out 9.75. That's the value of the function at that point. And basically, when I do outer g, it's going to create a matrix of basically all of these kind of intersecting points. So I say outer between the vector x, the vector y, and apply the function g to every kind of coordinate of those things. And then Plotly does something, it kind of flips the axes around on me, and so I have to transpose it, okay? But not that big of a deal. So anyway, what we can see is that in the upper left-hand corner of z is this value 9.75, right? And so if I just show you kind of like the top right-hand corner of z, this is going to be when x is negative 1.5 and y is negative 1.5, we get this. I think this is when, see now it's transposed, so I don't know which one's which. This is either going to be x is negative 1.5 and y is 1.45, or the other way around. Let's just kind of check. G of negative 1.5 and negative 1.45. Okay, so so this is, it goes down this column, and if I swap the other two, it goes over there. Okay, so we have 9. This value goes here, and this value goes here, and so Z is a matrix dimension 71 by 71, and that's enough to kind of get a surface. So I call Plotly, and I say we want a surface plot, and just like in ggplot, you save it, store it as a plot, and then you call the print command on it, and please work. Okay, there we go. Whoop. All right, let's it's very computationally taxing on your computer, so don't do this for your homework, but all right, so so it's pretty neat. You can like actually rotate this thing, and you can see that this is it's kind of a like this bowl shape, right? And then when you hover over it, this is it's a little bit tricky, okay? And when you it's too dark for you guys. Okay. Let me see if I can change the surface colors, but I don't remember how to do this. So let's go Plotly 3D Plotly 3D surface colors. Surface coloring. Oh, not Python. It works in R also. Can I change the colors? All right. I think, let's just see. Let's see if the I'm not sure. All right, you'll just have to squint. I'll figure this out here. Okay, but well, maybe if I hover up here, you can kind of see. Let me turn off these annotations. You can kind of see there is an ellipse shape, okay, as it should be, right? And then it also kind of shows the the line that's parallel to the x and the line that's parallel to the y and things like that. Okay, well, all right. So anyway, I'm gonna just start out at the coordinate -1, 1.5, x0 and y0 is -1, 1.5, and I'm gonna add a marker at x equal to -1, y equal to 1.5, and the z coordinate is gonna be the result of g there, okay? And there I know that marker color I can do orange, and it will plot, okay? All right, so this is man, my computer's having a heart attack here. Okay, so that's the location of our starting spot here. Okay, and what we're going to do is we're going to hold y constant at 1.5 here. Okay, and so this is a terrible way to do it. Okay. I don't recommend that you do it this way, but I've defined a new function called g at iteration 1, and it's a function of x, and where I basically say y is 1.5, and I say, well, now give me whatever else it is, okay? So I plug that in, and then we're gonna add a trace, basically a three-dimensional line, where x is going to kind of be this vector, the original vector that goes from -1.5 to 2, and we're going to add that trace there, and then y will just be equal to 1.5 for everybody, and then the value of z is going to be just the value of the function of x. All right, and then we'll add that to our plot. Okay. And so here, if I do this right, you can kind of see it has traced out basically at least part of the parabola right here, okay? And so we've started off at this orange point, and now I've got this thing that curves around here, and if I had graphed more, it would kind of curve back up. But what we want to do is we want to find, you know, what is the minimum of just this one unidimensional function here, okay? Just along this trace here, we want to just find what is the minimum here, and we hope that that will get us closer to where the minimum on the actual bowl will be, okay? And so for that, I'm going to just run the golden function on this function g iter 1, okay? So g iter 1 is a function of one variable x, and we're going to just start off, say, you know, starting here and here, what is the function? Oops, I have to source. Okay, let's try this again. Okay. Okay, so we're going to ask, we ask R to run golden section search, and so we don't actually care what golden section search does. Like, golden section search does, like, it chops it here and here, and then it finds a spot, chops it again, and chops it again. But we don't actually care. We just want to know what is the result of that, okay? So what golden section search does, I don't care. I just say, give me the minimum, and it runs through it, and it says, okay, 1.374999, okay? So pretty close to the real value of 1.375 that we found via calculus. You know, if I set the tolerance to be even lower, if I say tolerance, I think by default it's 1e -5, but if I say 1e -7 or something like that, okay, then it gives me back 1.375, right? So it just, so now that I have x1 is 1.375, I can add a marker there. And so the bottom of that blue curve okay, is right here. So according to our graph, once we've cut out this, this blue line, the minimum of that blue parabola is going to be right there. Okay? So, so now I have a new function. If this is now a function of y, I'm going to take g, I'm going to hold x constant, allow y to vary, and so I'm going to say x is 1.375, give me back what the function is here, okay? And so again, we do that. Maybe I'll change the color from blue to like, what's a good color?
Pink.
Pink. All right, let's try that. Okay, and so you can do it, computer, you can do it. All right, so so here it traced this out, okay, and then and now it traced, it says, okay, if we hold x constant at 1.375, what does the line look like here? It's going to be this pink line right here, okay, which is right here, and we're going to find, so that's getting us pretty close to the actual minimum. Like from here we can see, you know, the minimum is going to be over here. It's not quite there. It's kind of close. So so it's going to get us basically to the bottom of this portion of the bowl right here. Okay. So you know, we just do this iteratively. Okay. And of course, when you code the algorithm up, we're not going to like redraw these 3D surfaces that is taking my computer forever to do. You're just going to, like normally you would just have it calculate the things. I think in your homework I have you just draw kind of the segments on a contour plot, which is going to be a lot faster than what I'm trying to do over here. But just kind of for illustration, just so you can visualize what's happening, is we're just drawing slices. We're just slicing the paraboloid there, okay? And so we say, all right, here's my pink unidimensional parabola. What is the minimum of this function here? Okay. All right. So we're going to just run a golden section search on this function g iteration part b, and it says y is 0.1375. Okay. So that's kind of a coincidence there. We'll add a marker there and plot it, and so we should see an orange dot at the bottom of the thing. Okay, and indeed it is at the bottom there, but you know, it's over here and we want to get towards the bottom of the actual thing. So we just have to, we're going to iterate once more, okay? Or not once more, but over and over again. I think I only wrote the code up for one more iteration because, you know, this is very clunky, right? All right, and so I'm going to say, we're going to set y equal to 0.1375, and then we'll add a trace here. Maybe this time I'll do white, sure, okay. Sounds good. All right, and we'll do that. And I'm going to go ahead and just find the minimum there and add the marker, and then we'll go ahead and plot that. If we can handle this, right? Oh, come on. Okay, so there we go. And all right, so we started here. Let me turn off my... Okay, so we started up in this corner. We drew a slice, and we said, what's the minimum of this blue parabola? The minimum of the blue parabola is right here. And then we drew a slice. Okay, I'm disoriented. Okay, and then we said, all right, let's make a parabola, a pink parabola that cuts through that. And we said, what is the minimum there? and that turned out to be right here. And now that we have that, we drew another parabola in white that we can kind of barely see, all right? And that's right here, and we said the minimum there is right there, which looks pretty close to the, I don't know, on the bottom of the surface here. It looks pretty good, and you know, and probably, you know, if we wanted multiple decimals of precision, we can iterate, run a few more iterations back and forth. Okay, but anyway, this is the coordinate descent algorithm, and it allows us to tackle higher dimensional problems in a kind of a univariate fashion. All right. That's probably as far as we'll get as far as these optimization algorithms go in this class. If you take 102B with me, whether it's next quarter or next year or whenever, we'll look at more optimization algorithms, okay? Likely, so like gradient descent is kind of looking at multiple dimensions at the same time rather than just one dimension and things like that. But coordinate descent works in terms of you know, just boiling a problem down, okay? And so I think for you guys, it's just you get the top-down view and you just have the ellipses as part of your contour map, okay? And so you'll still get this kind of step pattern of where the function runs and operates, but just minimizing one dimension at a time, okay? When you code up your homework, if you haven't done so already, you're gonna wanna find a way to kind of redefine a function. You wanna be able to say, what is this function when I hold x constant, and what is the function when I hold y constant? I did it here in a very clunky way, redefining it at every iteration. Probably what you can do is within your loop, you'll define a new function when it's time to hold x constant, and then you'll define a new function when it's time to hold y constant, but then you can probably just keep that within one loop and have that, okay? So just some hints there. Okay, are there any questions on this? Do we feel okay about all of this? All right. Well, I guess we can just cut our lecture a little bit short today. I think that's all I want to say about coordinate descent. On Friday, we'll start talking other stuff, okay? So on Friday, I have lecture at noon, okay? It's going to be regular. I did send an email to the other class that I have to cancel the 1 o'clock class, but I didn't send it to you guys because class is still on at noon for you guys, okay? So that's going. So if you see questions on the piazza, don't be confused or anything. So we'll see you guys on Friday. We'll just end a little bit early today.